Let me ask.
Let me, no, they still see only this, they see. Duplicate slideshow, then try this one. Then should be okay.
We need a signature.
Yes.
And to the audience. Yes. Yeah, this one is from.
Yeah. Already realized. Yeah.
It's not open.
Yeah, I opened it. Yeah.
Actually, we is also working on nickelate.
Yes, I know. I know that.
Yeah, using DMIG and.
Yeah.
And Zhihai has done a lot of
Yes.
work on infinite layer.
Yeah.
Nickelate and also bilayer. Yeah.
Last time in Hong Kong, I guess.
Yeah. We met in Hong Kong. Yeah.
Well, we on the boat. Well, we have a boat trip.
Well, we went to the boat. That's true.
Yeah, a boat trip.
And no, but the boat trip was only a banquet, not
Only the bank in that.
not the conference.
The food is very good.
It's very nice.
One more minute.
Yeah.
我记得我说好说他你说来，我不知道他是好的。And doesn't know probably they will like to join, but I don't know he will. That's 1 minute more.
Yeah. It's central.
你好，能听到我的声音吗？扣上直播的，
可以。
好，可以。那我们现在开始。Okay, let's start. Good afternoon. So everyone, it's our great pleasure to have Professor Ilya Eremin to visit us. And first, I would like to briefly introduce Professor Ilya Eremin. Yeah, he obtained his PhD in Carson State University, 1999, and he went to Germany for his postdoc research. He won this Alexander von Humboldt research fellow, and he worked in Ruhr University of Berlin, right? In Germany.
Free University of Berlin.
Yeah. But in German, Ruhr.
Ruhr
University of Berlin. for 5 or 6 years.
For 5 years.
Yeah, 5 years. And then he served as a professor in Max Planck Institute for the physics of complex systems, and is as a junior professor. Then after that, he joined Ruhr-University of Bochum as an associate professor. Now he's a chair professor since 2020. You know, Professor Eremin's research mainly focusing on strongly correlated systems, low-dimensional electronic and magnetic systems. I think maybe most importantly should be high TC superconductivity, right? Actually, he's a well-known expert in high TC superconductivity. You know, he and his collaborators, such as Professor Andrei Trubkov, has made a significant contribution to the understanding of a lot of things in nickelates, including pairing symmetry, pneumaticity, and also magnetic orders. So he's really an expert in high TC superconductivity. So today is our great pleasure to have Professor Eremin. And today he will talk about this high TC bilayer nickelates. So Ilya, stage is yours. Let's welcome.
Yeah. Thanks very much also to the people who joined online. Yeah, it's a great pleasure to be here. And in fact, I'm actually visiting Beijing Institute of Math and Applied Science, the BIMSA, which is in Ruhr. And so I escape meeting, which is a very broad conference, mostly also including mathematicians, so to speak about physics. And actually, the title I chose and is basically diving deeply in the physics of the bilayer, mostly bilayer nickelate. So I don't have that much introduction, so therefore I feel a bit sorry for those of you who are not working on this system, but I will try. I have only a few introduction slides, but I will try to catch you up on the most recent development. Actually, that's a very exciting field, and I'm particularly happy to be in China because most of the experimental and also theoretical works is done here. So I'm very happy to be here and discuss physics of the nickelate. So I will be talking about 3 aspects. Most recent publication. Also, one of them was done in collaboration with Shanshin and his former PhD student, Jun Zhan, who is also here in the audience. All right, and this is Bochum, so it's a big university. So we have about 40,000 students, so it's the biggest university. So it's actually called Ruhr-University. That's a university of the entire region, which is located in Bochum, which is a relatively small city, but we have about 200 students in physics every year. So that's still quite nice. So we still have enough students to graduate. Okay, good. Okay, let me acknowledge. For some reason it doesn't work. Why it doesn't work? I don't know. Now it's froze. No, okay, it works. Okay. For some reason, okay, I will just by hand. It's okay. So, okay, so this is, let me first acknowledge my collaborators. So this is a work that has been done mostly with my group. That is, so I have 3 PhD students, Stefan, Marius, and Lauro, and the work that I'm going to present has been done mostly by them. I also fortunate to have a senior collaborator in our group who is also doing DMFT, but I will not present DMFT results in this work, maybe at the very end if the time permits. We also collaborate with another colleague who is an expert on the FRG, with whom we learned also this FRG method. This is Michael Scherer and Ayman Al-Eriani. And I have, of course, very fortunate to collaborate from people outside. We are fortunate to, gain some data from haiku events prior to publication, which allows us to be a bit, to know a bit more than immediately others, especially concerning the STM data. Also, the collaboration with June and Shanshin started during my visits in China. So there were some interesting questions that came from them during one of the conferences, and that resulted in a collaboration. And also Piyush and Luis. Okay, good. So that's my, let's say, short introduction. So that's from the review that has been written here in Beijing. This is a field of the nickelates. And just to tell those of you who are not working on the nickelates, so this bilayer nickelate came as a certain surprise to our field because if you compare the original motivation why people wanted to synthesize superconducting nickelate, actually that was a primary interest because as you see is that if your nickel has an oxidation 1 plus, then the valence of the nickel ion will be 3d9. And that resembles very much the oxidation of the 3d9 of the copper oxides. The original prediction was that it should be a superconductor, but the difficulty is that to realize an infinite layer nickelate, which is this system, is very difficult and only succeeded in 2019. And meanwhile, we know they are superconducting. This is also an active field of research. So meanwhile, under pressure, the system reaches 70 Kelvin, we still don't fully understand the system because it turns out that it's not exactly the same as a cuprate. So the physics is not a pure 3D x square minus y square. There are obviously some other orbitals involved, and we don't fully understand this. However, the particular surprise system is 327. Because if you look on the oxidation of this Rodolphson copper, because this would be a single layer, this is known since many years to be an insulator, magnetic insulator, and this one was not really well explored because of the complication of its synthesis, which still continues to be an experimental challenge, as I will tell you in a few minutes. That has if you compare the oxidation compared to the perovskite structure of this, you will realize that this is exactly in between. So it's been 7.5. And then initially people were not expecting it to be superconductor. And this is the system which you have. So you have nickel oxide layers, which are connected by the apical oxygen. Okay. And 4-310 is also very interesting. It also turns meanwhile to be superconducting under pressure, but TC is much lower and the pressure is much higher. So this is why experimentally it's very more difficult to study, especially the superconducting phase here. There's a lot of study and interesting magnetic phases, but I will primarily concentrate in my talk in basically analyzing only this system because of the time. Okay. Good. So that is the original discovery that has been made by Ming-Wang group. And as you know, some of you who work on nickelates know that the original motivation for Ming-Wang was to understand magnetic phases much better because it was not clear what exactly is a magnetic phase. But then once they put it in the pressure cell, they found a great surprise, which is actually keeps us busy and will keep us busy for several years, at least, I believe, is that the material becomes superconducting. And the primary reason from the crystallographic point of view why it becomes superconducting is that at the ambient pressure, the structure was claimed, and this again something which tells you that the field is very emergent, because I will show you a very is AM. This is a representative of this. So the most important part is that there is a tilting of the nickel or the 6 octahedra from one layer to another. And if you apply a pressure, there is a structural transition from the AM to the FMMM and later to the I4MMM phase, which is a pure diagonal state because FMMM is still partially or is still orthorhombic, but I4MMM zero resistivity. It was first shown by Liling Zhang and collaborators. And we know that this has been meanwhile reproduced by multiple groups. Moreover, if you replace one lanthanum by praseodymium, then it is believed to be 100% superconducting. The situation is more stable in this case. Okay. Now, let me tell you why. Let me show you one very recent slide. So it's actually since the beginning of this year, there has been growing doubts whether the actual phase is AM. So this would be this phase. So it's orthorhombic, but important is that there is a 2-position nickel 1 and nickel 2 in the unit cell in the plane. And they were considered to be equivalent. In this case, crystallographically different, but electronically equivalent. And that has been put into question. There has been one paper by the group of Hirschberger from Riken. There has been recent data, which is just 1 month old. However, one of them is coming from Takura group, also from Riken, but they grow a very nice single crystals. And there is also Stuttgart group has found also similarly the same issue, that actually the actual symmetry is lower than the AM-AM, and the symmetry is AM to M. So that means that this nickel 1 and nickel 2, they are have a slightly different charge. And moreover, there is already at ambient, at room temperature, so they said that the transition to this phase probably happens. So the Stuttgart group claimed that the transition to this phase already occurs around 600 K. So it's basically everything, magnetism and all the other phases that appear, they appear not in the AM, but actually at the low symmetry, which is AM to M. And actually, that also gives rise to some polarity along the B0 axis, which is shown here. So that's very interesting, and I can tell you later that actually for us it's a good news because we were trying to understand the magnetic and the charge phase in this system, and it turns out that we can largely reproduce the experimental data, except we cannot reproduce the temperature dependence, and I believe that the AM to M phase is something which gives things, explains better. Okay, so however, to study system under pressure is difficult, especially if you want to do some thermodynamics. So we gain a lot of information from studying films. So it quickly turns out that if you grow, you can grow films tetragonal from the very beginning, provided that you grow them under some compressive strain. So you have to choose a particular substrate which provides a compressive strain, and then it becomes superconducting. That has been shown by Harald Wang and also by the one Chinese group, with the original data, where they growed on lanthanum strontium aluminum oxide, which provides something like 2.1 compressive strain, where they reach superconductivity. Let me, however, mention that the most recent progress on the symmetry of superconducting gap, on the measuring the superconducting gaps, that comes also from Sustek group, which managed to grow very nice films, and the highest superconducting transition temperature, onset temperature is 63 K, where there has been a very convincing evidence and a series of papers showing a very nice transition. Furthermore, there has been already meanwhile ARPIS measurements and STM measurements that are not the first. I will be talking about the first STM measurements later today, made by the group of Haihu Wen from Nanjing. But all the information about fermiology, which is needed to know in order to know superconductivity, that comes from the thin films. And that what is importantly is that they see that there are these bands that I will be discussing also later theoretically, which is alpha, beta, and gamma Fermi surface sheets, and the gamma pocket is indeed crossing the Fermi level, forms a kind of a waterfall structures, so which is very interesting. Now, just before I came here to Beijing, there has been another 2 papers that appeared just last week, which is now coming from Haifei group, which actually managed to grow superconducting films even in under a stronger substrate, minus 2.14. This is, as you see, neodymium aluminum oxide substrate, which also find the onset superconductivity of about 60 K. Also managed to measure, shown some, one of the problems with the thin films is that you need to show that superconductivity is really a thermodynamic features and not a filamentary. So they provided this evidence, and they also measured the fermiology of the system, measured the size of the gap, which is consistent with all the other values that has been subtracted from the other thing. And even more, they saw how the fermiology changes as a function of the substrate. So that's really, we see that even now, 2 years later after the initial discovery, there are still exciting findings that are going on. So they could study how the fermiology changes as a function of the substrate, which is very, very nice. Okay, so that's where the information about the superconducting state is coming. Okay, so that is where we are now. So we know that it's superconductivity. We know the sizes of the gap. We know what is the fermiology necessary to get a superconductivity. So it's a necessary but maybe not obligatory condition. But nonetheless, this is where the model has to start. Okay, and now this is the end of my introduction, if you want. After flashing this, let me concentrate on the three topics that we have been working on over the, let's say, last half a year, which resulted in these three publications. So first of all, we wanted really to see whether STM data are unambiguously showing us the symmetry of the superconducting gap, or we have to be careful about this. And my argument will be you need to be careful in interpreting the STM data and make it consistent with the RPIS. Then I will be talking about the other question, is that something that we discussed was, well, in this system, it is known that the system is magnetic when it is in the orthorhombic phase. However, if you look at the fermiology, it looks surprisingly similar to the one we see under pressure, or we expect to see under pressure. So then we ask a question, and this is actually a collaboration with Sishan Wu group and with June, is can we expect that maybe even orthorhombic material may become superconducting? And we were discussing it with using the method that can self-consistently describe magnetism and superconductivity together, so with FRG, functional renormalization group. And then the other state is that we were diving in the studying the origin because it's known that there is two transition at the parent phase. There is a magnetic transition, but there is in the resistivity scene another transition, which is interpreted as a density wave transition, which is not seen in muons. So it means it's probably a purely charge origin of the transition. And furthermore, they show a very different behavior if you apply pressure, small pressures. So that has been done by also Mirza group. They saw that the spin density wave transition is going up. And that has been now confirmed also in this study of this AM2M phases. And the charge density wave transition is going down. And so that's very unusual. And this is also something we try to understand with Lauro. And I will speak about this at the end. Okay, so now I think from the thin film data, there is a growing evidence that the symmetry is S-wave-like. There is a combination of LCM, there are also RPIS data, especially the measurements along the nodal direction of the dx square minus y square, and seeing that there is a constant gap there gives you some evidence that very likely the gap is not a D wave. Nonetheless, if we look into attempts to study the symmetry of the superconducting gap under applied pressure, it turns out that the situation is at the moment a bit ambiguous, because the only experiment that could be done until now under pressure are point contact spectroscopy data. In this case, essentially, you make an SN junction. And then you try to analyze the spectrum that appears, and then you have some also you can study the angle dependence depending on the rotation of the junction, and somehow what the conclusion were not uniform. So one of the group claims that they did see a D-wave symmetry, a strong signature of the D-wave symmetry. While the two other groups, which are from China, more concluded it's also kind of anisotropic S-wave. One could in general put a grain of salt in all these measurements, because if you look at the data, you will see that the enhancement of the signal is only about 10% of the total signal. And that tells you that this junction are in a strong diffusive limit. And the theory analysis that has been done, of course, has been done in a clean limit. And that, of course, raises a question, how reliable are conclusions if you use formulas which are strictly speaking valid in a clean limit to a junction which is in a strongly diffusive limit. So, but nevertheless, there is some ambiguity. And now ARPES at this point tells us it's very likely an S wave-like shape gap. And now the data start to converge. But if you look at the STM data, also if you look at the behavior of the IDV curves that you see in STM, you also, if you do, let's say, a simple-minded Dines fitting of this, you also come to the conclusion, and this is also the conclusion that the group of Haihu that the first group that did these measurements, and we also were part of it. So that comes out like to be an S wave. However, it's assuming that you have a simple Dines-like fitting. We know that if you deal with the STM, it's important how the current is tunneling into that. And this is especially in a multi-orbital system. And we know that the nickelates are multi-orbital system. So that's, let's say, a model that is kind of considered to be the low energy model, let's say, by majority of the community. So you have a basically you have a EG manifold, so it's 7.5 or 3D8 if you assume that there is also oxygen involved for ligand hole, and then you're dealing with EG manifold, so you have a dx square minus y square and the dz square orbitals sitting on the nickel, and then because of this apical oxygen, you have a strong hybridization. And the strong hybridization yields that you have a strongly splitted, so you can work in this mirror symmetry. You can use this layer structure and introduce a mirror symmetry and introduce mirror symmetric or anti-symmetric combination of the electronic states, and then you end up with 4 bands, so 2 orbitals, 2 layers. If you diagonalize it, you get 4 bands. And then you can still identify, despite of the hybridization, you can still see that the bonding, in this case, dz with dz square like orbital is still crossing the Fermi level, or maybe not. That's something that people are still discussing. While if you, and the delta pocket, which is also originate initially, if you look at the on-site energies, originate initially from the dz square, but it changes color, so it means there is a lot of hybridization, but it doesn't cross the Fermi level directly. It's only degenerate exactly along the M gamma point. And then you have a dx square minus y square. So if you look at the Fermi surface, this is the Fermiology that you have. Sometimes people were wondering whether this gamma pocket is crossing the Fermi level. So it's known that in a bulk crystal, it doesn't. At ambient pressure, and I will be talking about this as well. Then you are dealing with this topology, Fermiology. And it's actually quite interesting because in principle, you can have a legitimization of different type of model. You can consider Z square to be, completely occupied, being essentially localized like. Of course, it's not what comes out from the DFT, but that's what one part of the theory assumes. You're effectively dealing with the dx square minus y square, which is strongly splitted. The variety of the models that you have currently on the market. So essentially, but what is important is that I think the conclusion is that you have to work in the situation when the z squared is much more correlated than the dx square minus y square, independent whether you take a one extreme view where z squared is completely localized, or even if you think it is itinerant, but it's still closer to half filling, so it's more correlated. Okay, so that's a model. And now again, that's a kind of introductory part. You ask yourself, okay, so what kind of pairing I get? And then it turns out that depending on the methods, models, and so on, people get very different symmetries. I think if you start from the, let's say, itinerant perspective, what most likely you get is a S plus minus symmetry. And that essentially in the real space means that this is a pairing between the layers. So essentially, you have a superconducting gap where you really form pairs between the two layers. And in this case, if delta perp is larger than anything what is happening in the plane, and if you do this unitary transformation to symmetric and antisymmetric bases, then delta perp comes with a plus in the one and the minus in the other. So this is how you get this S plus minus order, because if you recollect that these are the bonding bands and this is the anti-bonding band, and then the S plus minus tells you that it has to change sign between all bondings and all anti-bonding bands. And that's one of the realization. And that requires that the delta perp is larger than whatever is in parallel. And it's actually very interesting that if you do an FRG analysis, in this case, the magnetic phase that is seen in the system, there are some details to that, but the instability is indeed connected to this wave vector, which connects this basically this pi over 2 in this tetragonal unit cell. It will be a pi over 2 wave vector, and this is the one which also gives rise to the magnetic order. And important is it's also antiferromagnetic between the layers. Okay. So there has been other proposals, and these other proposals are telling you, well, you still can have a situation that the interlayer correlations are important. In this case, your interlayer becomes larger than the interlayer gap, and then how to live in this situation. And the problem occurs in this case is that essentially you have somehow to deal with the situation that you have to overcome repulsion in the model. And the way you do it is in this case by creating a dx square minus y square symmetry of the superconducting gap. And that brings you more or less to this picture. Yeah? And that is what people were discussing in the context of the bilayer nickelate. Now let me come to the problem of the tunneling. And the problem of the tunneling is that if you come with a tip, then of course it never really hits the sample. Usually you try to avoid that it hits the sample. So the tip is always located at a certain distance with respect to the surface. And if you look at the extension of your one-year orbitals, especially here, one has to also keep in mind that in these models, the oxygen is somehow unimportant, but it's not true, because we know that there is a hybridization with the oxygen. But in this case, you integrate out the oxygen state to make it a part of your dz square and the dx square minus y square orbitals. Because effectively, if you look into the structure of your Wannier function, you realize that you need to extend your Wannier function well beyond the central position of the nickel, and it includes all the oxygen states as well, right? And if you look into the dz square, you see that there is a strong involvement of the oxygen p states, pz states, and it's very extended objects. But so that's to the extent that the oxygen states are important in this case. And again, if you would do ARPIS, and this is what has been done, you will see a lot of contribution from the oxygen, but they are included in this effective low energy model. But what is important for me now is that if you, let's say, suppose now you come with a tip and the tip stops in a certain distance with respect to the surface. So it means, for example, here or here, and then effectively the tunneling, even if the STM tip itself is the S-wave function, will have a different orbital width, how it will tunnel into the system. And the way to do it is not to take a lattice Green's function, but actually take a continuum Green's function. So it means that you take really a lattice R-dependent Green's function, which do take into account the matrix element, and this matrix element in this case are your Wannier function, which is here. So it's basically whatever you calculate on a lattice level in your Green's function formalism for your lattice-based model will be dressed by the corresponding Wannier function when you perform the tunneling. So it's in principle a rather simple idea. So, and when you do this, you realize that when you do STM in experiment, you will be mostly tunneling into the dz square orbital. And that immediately tells you that there will be some differences. So first of all, what you notice is that in this case, even if you have symmetry imposed, dx square minus y square symmetry of the superconducting gap, you will see that actually in this case it will be hard to sometime to distinguish between S and D wave, simply because as tunneling occurs via the z square orbital, and the contribution of the nodes, and the nodes are exactly where the main part is coming from the dx square minus y square orbital will be suppressed. So that's somehow a bad news. It tells you that in the STM, it will be hard to say whether the symmetry is S wave or D wave. However, it can also be considered as a good news because in principle, you can try now to change the position of the tip with respect to the surface. And by doing this, you will actually be able to visualize if the nodes are indeed there or not. But even more, here what we do, since in the STM, they don't know, they see two gaps. So this is the data of the high-fluence group. And now let's assume for a moment that the gamma pocket doesn't cross the Fermi level, right? For example, and then you say, okay, so now I have two possibilities where the main gap is. And then you can start from the situation that the larger gap is in the alpha pocket and the smaller gap is on the beta pocket. And then you run the simulation as a function of z, as a function of the tip height in this case. And then you find an interesting situation that actually that it's very hard to reproduce the experiment because you start when the tip is very close and then you see this one. But the moment that the tip moves away, you start to see that the coherence peak on a beta pocket, which has a smaller gap, would have a smaller gap, would start to increase and start to be completely incompatible with experiment. Which effect, and this is clear why, because beta pocket has a lot of z-square contribution, much more than the alpha pocket. So which basically yields you to conclude that although it's hard to distinguish between S plus minus or D wave, but what you can certainly say is that it cannot be the case that the largest gap is sitting on the alpha pocket. So it must be on the beta pocket. And indeed, if you do this calculation, if you assume that the larger gap is sitting on the beta pocket, which has a lot of contribution from the z-square, indeed, in this case, you when you come to the reasonable value of the height, like 5-6 angstroms, this is more or less correspond to experimental situation, you see that indeed your data start to be much more close to the experimental situation. But again, still, even in this case, it's very difficult to distinguish between accidental S plus minus with accidental nodes and the D wave, because in the D wave, you see case, you can have a completely flat region here. Whereas in the case of S plus minus, because of accidental nodes, you still see a V-like shape. So again, the low energy, low bias behavior of the STM can be, in this case, misleading. But what is interesting is that if you are able to shift the position of the tip and do measurements at different positions, it can provide you a momentum selective information. Now, if we believe that the gamma pocket is indeed cross the Fermi level, like ARPIS suggests, then the situation is again changing. In this case, you have to assume, because experiment tells you that there are only two superconducting gaps, effectively you have to assume that in this case, one of the largest gaps sit on the gamma pocket. And then the other part that you also then conclude is that you can only have an S plus minus superconducting gap, because in the D wave, if you put a D wave on the gamma pocket, then it actually turns out that on average, the gap will be very small. And that is why the spectra that you deduce in this case then do not make any plausible comparison with experiment. So at the end, if you believe that the gamma pocket crosses the Fermi level, then the only explanation of the experimental data would be that it is an S plus minus. And again, what we, however, suggest is that in order to make an ambiguous confirmation, what you need to do this height dependence measurement. So you need to vary the tip position and try to measure the IDV curve as a function of pressure. So that's just the first message. And, been talking to the STM groups here in China who are in a position. So they are trying to do this. But of course, you need overall to know that this tunneling matrix element is always exponential dependent. So that's a very challenging experiment by itself. Anyway, so this is the part related to the symmetry of the superconducting gap to interpretation in the STM. But I think, again, the current conclusion is that it's very likely S plus minus, which is good news because most of the theories are also predicting it should be an S plus minus. Now, let's ask another question. And the question, as we know, that if you, let's say, forget for a moment about the ambiguity about the structure, But important is that whatever it is, AMMM or AM2M, there is a spin density wave transition into the double stripe magnetic order. And as a function of pressure, these two transitions, which are about 30K difference in the parent material, the ambient pressure, but they start to split. So spin density wave is going up, density wave transition is going down. I will be talking also about this. And then there is this I4 MMM phase. And then the question, however, if you now look at the fermiology, and you look at the fermiology at high pressure, that's what you've seen until now, right? So you have this alpha, beta, and the gamma pocket. And you compare it to the fermiology of the orthorhombic phase. It actually turns out that the fermiology is very, very similar. If you just take into account that you just need to fold your original tetragonal Brillouin zone, because now you have 2 atoms per unit cell. Yeah, so you have basically 4 atoms per unit cell, right? And if you do this, so then you see that there is a folding. So there is this structure appears. Your gamma pocket now appears in the middle here because it folds back into the gamma point, and so everything. So it looks very, very similar. And so you can ask a question now. Why is that? Can it become superconducting also? So why it does not become superconducting? Because in principle, one of the arguments that sometimes comes from the strong coupling theory is that once you apply a pressure, what is actually happening is that the interlayer exchange interaction is going up. At the same time, you would naively say, well, why then tetragonal doesn't become magnetic and only superconducting? So it would be nice to understand what is really going on. And this is where the part of our collaboration with Shizhen Wu and Jun Zhang. So essentially, we just said, okay, we know it's not superconducting, but we can still run an FRG code both at the ambient pressure and at the high pressure phases to see what's going on, what is the leading instability. And then you have a certain value of U, typically 4 electron volts or something like this. And then you start to vary the Hund coupling to see what is going on. And then what you notice is that at high pressure, indeed, the largest part of the phase space is taken by superconductivity, which is S plus minus superconductivity in this case. And however, if you raise the J, it becomes also a spin density wave metal. The same, by the way, spin density wave stayed as before. But if you do it at the ambient pressure, you still see that the overall phase space now is dominated by the spin density wave, but you still have a superconductivity, still for reasonable values of the J. Now, what is the difference between these 3 curves? The difference between these 3 curves is again the position of the gamma pocket, because since it still has been kind of ambiguous, we played with 3 different parameterizations. So gamma pocket being well above the Fermi level, but in this case, it seems that it's not a good good situation, neither for this spin density wave nor for superconductivity. When you have a gamma band which touches the Fermi level, it actually turns to be the ideal situation for superconductivity. The system really wants to become superconducting in this case. And it's actually independent whether you're at ambient pressure or you're at a high pressure. So essentially, in both cases, when the gamma pocket just touches the Fermi level, it wants to become superconducting. And if you now go to the gamma band below 50 MeV, below the Fermi level, then it's actually more favors spin density wave state, right? So, and that is again something that has been well understood. So now I will be talking about this, why the relative scale is changing. So still you have this interesting interesting coincidence that at ambient pressure, superconductivity, despite of this manipulation of this position of the gamma pocket, lies at much smaller range of the J, whereas for the high pressure, superconductivity is taking over. So you want to understand it better. And you see that despite of this, let's say, different position of the gamma band, which by the way was very well understood by the previous works, which has been done here also, and also by Hamburg group, which essentially the argument was that if you are for a moment only considering the tetragonal phase, what you see is that when there is no gamma pocket, then there is only one leading instability, and this is this pi over 2 pi over 2 instability, spin density wave. While if you introduce this gamma pocket, this further increases the magnetic susceptibility in the odd channel. That is the one which will be supporting the S plus minus. Once this gamma pocket gets too large, then you basically suppress superconductivity, and this is where that you see will go down. So that's what purely tetragonal. And in principle, the same is true for the orthorhombic, but there is something else. And let me now try to tell you what is this something else. This something else is frustration. Because if you now actually start to think about tetragonal system, you know that there is a wave vector pi over 2 pi over 2, but there is equivalent wave vector pi over 2 minus pi over 2. And they are connecting different position at the Fermi surfaces. So, or in the Brillouin zone. So which effectively tells you that in the tetragonal system, you have two wave vectors which are frustrated. So they frustrated with each other, so they compete with each other. So they don't know which magnetic order they want to set in. And this is what you see very nicely with the FRG, which is picking this up, because what you effectively see that if you do it at the high pressure, you see that you play around again with this position of the gamma pocket, but effectively you see that once you have this strong frustration, what effectively is going on is that these two wave vectors frustrate, and it's easier for superconductivity to take over. So, because frustration suppresses the long-range magnetic order. Whereas if you look at the ambient pressure, you see from the very beginning that these two Q vectors behave very differently, because already the structure has chosen for you which wave vector it wants to have, because it will be just 0 pi and not pi 0. And that is you see also in the FRG flow, because you see that these two different instabilities, magnetic instability, behave very differently. So the anomaly between this pi over 2, and pi over 2 minus pi over 2 is increasing. So magnetic one is starts to dominate, whereas and therefore superconductivity has no space to develop. And that is also seen as a function of the position of the gamma pocket. So effectively, there is a magnetic frustration, and this is an important aspect which needs to be present in order for superconductivity to win. So once you move to a tetragonal phase, magnetic frustration are large, fluctuations are big, and that is what does not allow long-range magnetic orders to set in. Whereas in our orthorhombic system, it's easier to build up magnetism. However, in the tetragonal phase, superconductivity is taking over. So it's again confirming this idea that in unconventional superconductors, you always need to suppress the dominant magnetic instability. And once you suppress it, and in this case, here's a way to do it, is to go to a tetragonal phase, and that will rise to superconductivity. Okay, so that is also what then you can put in this phase that I already presented to you. But that gives you also a prediction. And the prediction that it makes is that now you can do a hypothesis. You say, okay, so you can do two types of experiment given the current situation of the experiment. So you can start from the thin film, which we know are tetragonal, but now you don't apply only compressive strain, you also apply uniaxial strain. And if you apply uniaxial strain, you expect that it should become then magnetic, because you will be suppressing superconductivity because the system will not be longer tetragonal. Or you can also try to do another experiment where you apply a strain to compensate orthorhombicity, so compensating strain. It's more challenging given the structure of these bilayer nickelates, but in a theory you can do it. And this is what is effectively we done, where we just took the band structure from the orthorhombic case, applied a compensating strain, and then did a relaxation, and then afterwards again did the FRG calculation. And that we effectively see that once we do this critical scale, when superconductivity rises is essentially shifting. So it actually moves towards more tetragonal situation. So, and this is also somehow a hypothesis, which would be nice to check because it will unambiguously put a connection between superconductivity and magnetism. Because again, since there is a structural transition in between, it's still somehow a question whether the magnetic phase is really a parent phase. But doing this experiment, you really can prove whether it's a parent phase or something else. Okay, good. So then let me, in the last 6 minutes, discuss another aspect. So now let's look a bit closer into the magnetic state and try to understand what is this extra charge density waveform. Let me first again come back to the story of the gamma pocket, because again, here from Beijing, there were calculations which were saying that if you do DFT with hybrid potential, then the gamma pocket shifts away from the Fermi level. So it basically appears below. In fact, you can just take a DFT, or you can just take tight banding that you derive from DFT, which contains this gamma pocket, and then put it in a Hubbard-Hund, but then you just do a Hartree-Fock calculation, just looking into the band renormalization due to static U. And you get exactly the same. So you basically see that once you have a non-zero U, it immediately shifts also the position of the gamma pocket below the Fermi level. And you try to understand what is the origin of this. And you also can play with crystal field splitting and also with the U. So here the results are presented with a crystal field fitting. But what you effectively see that eventually what happens, and it's also as a function of U, that the reason why the system wants to gap out the gamma pocket is because the dz square orbital wants to become exactly half filled. Because if you start from the DFT, the filling is about 0.96, but so that's kind of when you plot it on the itinerant level. But once you include Hubbard U correction due to the, even on the Hartree-Fock level, you see that the filling on the dz square wants to become half filled. And that's nice because effectively it also tells you that the main correlations are playing on the dz square orbital. At the same time, if you look into the occupation of the dx square minus y square, you see that this simple-minded Hartree-Fock correction already tells you that it wants to become just quarter filled. So it wants to become more itinerant. So even at this level. Again, let me tell you that we also, it's, since there are two parameters, U and J, if you also do not then just simple-minded Hartree-Fock and do, do something more advanced like Trilex, which we also did, the results are a bit different. But I just wanted to tell you that even with this itinerant perspective, you agree that the dz square is more correlated than the dx square minus y square. Okay, good. So then, okay, so once you do this, so you know already that before a spin density wave state, in this case, it's a weak coupling calculation, which is, and the instability is driven by this pi over 2, or in this unit cell, it's a 0 pi. And indeed, you develop such an order, which is a spin density wave order. And you see this Fermi surface reconstruction that appears due to the formation of this 0 pi order. You can see that the large gap is developing on the dz square orbital, so because it's more correlated. But you still have a residual Fermi surface because it's essentially comes from the dx square minus y square orbital contribution, and there is a band folding. Okay, so you also can identify where the spin density wave gap might open exactly. And now here comes a question: is that how to compare it with the RPS? So to compare with the RPS, you need to know that usually in RPS, because of the Fermi function, they cannot really cut at particular energy. They perform some summation. So basically, what is shown here is, so here is really a cut at 0 energy, right? So at the Fermi energy. However, here, what we did is that in order to emulate the experiment, we actually integrated out a narrow spectral weight. So we integrated out plus minus 30, 40 millieV. We integrated the spectral function and then plotted its normalized sum. So this is what would be something like a Fermi surface map, that an RPC. And then you compare again. So one of the interesting statements that has been in the experiment, so there has been two groups. One is here by Donglai Feng group, and another one from which is published already in Nature Physics, is by the group of Damascelli. So the claims they made that actually, so first of all, you indeed see this this folding. So they see this, and there is this T beta. So you see this very nicely also, this reconstruction, and this reconstruction is actually indeed comes out from the 0 pi wave vector. You just need to take a corresponding folding of your bands, and then you see that's exactly corresponds. That's actually, by the way, something that was ambiguous in this experimental paper, because they claim in order to get these structures, I need to suggest that there are two kinds of nesting. In reality, you don't need it. So it's all done with the same Q vector. You just need to find from where that's actually folding is taking place. So if this one is appearing here, the other one is just appearing here. But then there was another statement that they made. They said that the large gap they see is actually coming from the dx square minus y square orbitals. And that is something you need to take into account, that there is a true gap, and this gap is actually coming on the states which are not only at the Fermi level, and largely not at the Fermi level, because they sit on the dz square orbital. But of course, you do have effects for the x square minus y square pockets as well. And what is exactly happening is the following. In order to form a folded band, you need to take some spectral weight. So in other words, what is actually happening is that when you do this folding, some spectral weight, of course, has to be taken from here and from here. And this you very nicely see if you now plot the MDC along the gamma m, for example, direction. You clearly see that once, and this is the reduced temperatures, sorry, and then you see that the lower the temperature is, the more spectral weight is taken from the true band to the folded band. And so something that our interpretation is that what they claim to be a pure spin density wave gap is actually a result of the folding of the Fermi surfaces. Okay, so that's our kind of discussion with Damascelli, because Damascelli has a kind of a very exotic explanation for his data. Anyway, but now they continue to lower the temperature and allow for charge order to develop. And there you see that there is another order which develops, because it turns out that this double stripe is energetically unstable towards forming an additional intra-unit cell charge density wave order. And the consequences of this intra-unit cell charge density wave order, that it suppresses the magnetization on one of the sublattices. So you want to move towards spinless stripe, double stripe. Of course, so, and then what happens, it means that below a certain temperature, again, where exactly this temperature depends on the microscopic details. It can shift as a position of the crystal field splitting. But what is essential is that at certain temperature, your magnetization will split. So there will be magnetization of one sublattice starts to increase even faster, whereas the magnetization on the other sublattice start to decrease. So you start to suppress it to form this spinless double stripe. And in addition, you will have a formation of the charge order, which appears here. And then you could check whether you see something on the fermiology. You don't see this, so because everything is mostly driven by the magnetic part. There is no additional contribution because it's mostly intra-unit cell order, so you cannot see it in the additional fermiology. Okay. So this is the situation. I already discussed with Shenshun that there is Wu that there are still difficulties that we need to address, but I think here I have to say we did the calculation for the AM phase. Actually, we know now that the phase is AM to M. So I have an answer to that if somebody is interested. But in this case, what will happen is that you have already from the very beginning, this green and red will be different already. They have already from the structure slightly different charge. So it means that there is already an intra-unit cell charge order appears from the very beginning. So it means that magnetic order sets in already in the presence of the charge order. So the actual transition of the charge order happens at much higher temperatures. So this is what we believe right now. Okay, so this is a conclusion. Sorry, I might be a bit too long. No, I think it's still okay. Okay, so that is the three messages that I have. Is that so? STM is very interesting experiment, but you need to take some care, and moreover, it can produce some filtering effect, which might be interesting to discuss, not only in nickelate, but in any other material that plays an important role. For example, for trilayer nickelate, that's also to be known features the spin density wave. If we believe we deal with the S plus minus superconductor, this magnetic order with pi over 2 pi over 2 pi is really a parent phase. So it really is the one which gives rise also to superconductivity. An ambiguous proposal would be apply uniaxial strain to tune the competition. And if you really look into the detail of the magnetic order within this itinerant Hartree-Fock mean field perspective, of course, again, what you need to know is that you cannot predict the temperature of the transition. For that, the model is, of course, it's just a Hartree-Fock, but you still can analyze the consequences of the magnetic order. You see that there is the charge order. It wants to develop also to form a spinless stripe order and would be further interesting to study this state. Okay, and this is also another reference. Okay, I have another part related to the Strelex, but I decided that it will be too much. Okay, thank you very much. Thank you also to those who are online. I hope you were able to hear me. I'll try to stay close to the microphone. Okay.
Okay, thanks for the wonderful talk. So now the session is for discussion.
Should I now? Yeah, there is a chat.
This is maybe we can have question from here first, from here, and then I will look at the chat here.
Okay. I also. So far, there are no questions in the chat.
Yeah, but you know, there's another.
There is another.
We'll check the we can close this.
Okay.
Yeah, I will check the questions.
Okay. Good.
Any questions?
The question for the last part when you mentioned about the charge density wave and the spin density wave.
Yes.
What you mean? As I heard you mention that in your calculation, you already set some kind of a charge density wave in to do the calculation.
No, for this case, no. So in this case, we just allowed because when you do the Hartree-Fock, of course, you essentially need to allow certain
initial.
Right.
But apparently
we don't have an instability. So let me put it like this. So if you analyze the corresponding charge instability, you don't see this. You don't see, because usually, if you look at the paramagnetic state, right? Suppose I start from a paramagnetic state. There I see that there is a very clear instability in the spin density wave channel, because I see that my susceptibility likes to diverge at 0 pi, right? So that is one I know. So that is the orders that I set in. That is initially suggested. Then we knew from experiment that translational symmetry at the density wave transition is not broken. So then the only other order that we allowed is the intra-unit cell charge order. So we allowed this order to develop, and indeed in this case we see that it develops at a low temperature. However, we don't see this order at high temperature to be in. So when we compute the charge instability on a weak coupling, we don't see. However, once we perform a reconstruction of the fermiology, we see that both charge and spin susceptibility develop a Q equal to 0 instability. And that is this intra-unit charge instability. This is this intra-unit cell charge order. So that's partially a result of the folding in this case, that you develop, so there are these regions and there is some scattering between these regions, the low Q, and that gives rise to the additional charge modulation. However, it's not something very conclusive, I would say.
Yeah. So I think this charge order is kind of induced order from
It's an
this
induced
statement.
order, right. It's an
Because you
induced.
have high zero order, right? Double means zero, cube is zero.
Cube.
That's the
Yeah. But I mean, if it's like induced order, probably I would think that maybe this induced order will somehow like
Okay, so
show up symmetry at the
I
symmetry or
well, that is again, it can, but it doesn't have to be. It really depends
not
on.
really true.
There is no symmetry argument why they should appear at the same time. But if they appear at the same time, then very likely it will be a first order transition, because once they are coupled, then very likely it will give rise to a weak first order phase transition. Okay, but here let me tell you another part. You know, in the why I think that there is a similarity with 4310, because in the 4310 the magnetic wave vector is incommensurate. So it means that if I take a double Q of this, it will be another incommensurate wave vector. And this is what you see. But here in this orthorhombic unit cell, the magnetic wave vector is 0 pi. So if I take a double Q, it's Q equal to 0. So to some extent, it's also a double Q instability of the induced by the spin density wave order, except that here this 2Q will be 0, right? Because it's 0, 2 pi. So it's a reciprocal wave vector. So that is why this is intra-unit cell. So the system cannot develop another incommensurate order because it coincides with Q equal to 0.
Yeah. Maybe I have a following up question. When you have this charge order, right, you see that one side has nearly vanishing magnetic moment.
Well, very small. We don't have exactly vanishing.
Yeah, very small. So because this is just because of the occupation of dz squared change,
right?
Or so what is the physical reason for this? Why it's become very small when you decrease the temperature?
Yeah, so what effectively happens is that, okay, so there is a component, so it's true. So there is a z square and there is an x square minus y square.
Yeah.
And the magnetization on the x square and the z square, it doesn't sum up, but essentially it's in one lattice, it sums, but another one, it's
it will cancel.
It will cancel.
Oh, I see.
So that is what we find. Yeah. So that because the total. So basically, in one case they add, and in another case they so one there is a charge order. It basically yields a compensation.
You mean the contribution?
So you have
the magnetic moment for
yeah. So
atoms are comparable.
Right. Yeah.
Ah, I see.
Yeah. So it is well. It's not exactly comparable. They're still z square is still larger.
Right.
I might have a. I probably have somewhere. No, unfortunately, I don't have but I have it in a paper. We can look. But there we give the numbers. So it's about one. I would say 2/3 of the z square. So then the x square there is also.
So just the one of the changes sign.
Right.
Then they will cancel.
They will cancel each other.
Okay.
Yeah,
Okay.
yeah.
So more questions? Sure. Yeah, I have another one. When you compare with experiments, right? This spin density gap, you in the nature physics arguments, they only show the form surface. In principle they can see the
right.
gap.
Yeah. So this if they would go below,
yeah,
they would be, and this is what I think Dong Lai Feng group did, or Zhou group did. They looked also below.
Yes.
The problem is that in this type of experiment, they were interested in the dichroism. And I think when they do a dichroism, they can only do the Fermi surface maps. Okay. They cannot really look well below the Fermi level. Yeah. At least I don't remember seeing the maps. I mean, we can check again, but I don't think I've seen the maps.
Yeah, in principle, if I look at the form surface nesting, right? I think the gap maybe it was around slightly away from the diagonal direction. I mean,
Right. So in
yeah.
principle, it will be somewhere here, right?
Yeah, not
Because
just around along this kind of touching point.
yeah, right. So this is here, right? So right, this no,
These two, yeah.
Yeah, right. So you need to
Yeah.
connect. I guess you need to connect from here. I think my battery has died. Oh no, sorry, I'm just pressed. Yeah, I think you mean here to here, right?
Right.
So from here to here, right? So this is where the main gap would appear between here and here.
Right. Not just for the dx square minus y square orbital, right?
Right.
Horizontal.
It will be also for the dz square, right? But our argument is, despite the fact that the main gap will be appearing on the z squared, even for purely dx square minus y square, you will see the effect because you have the folding. And so even there, the spectral weight of the Fermi surface has to go down. Because you need some spectral weight to form a folding.
So they clearly identify the folding for the beta pocket, but they did not identify folding for the alpha pocket.
Well, it is here. It is here. I think they have another picture where they actually argue. So they said there is a T beta and there is another T alpha.
I see.
Yeah, this is this one. You don't see it very well, but it's more, in our case, it's much more rounded than in their case. In their case, it's really like very flat. I think this one.
I see.
I think on the other figure in the paper, they identify this wave vector.
Yeah. From this result, in my opinion, we don't need, I mean, their papers, they argue these 5 spin-on states and fancy stuff. This is just some folding.
This is what, in my opinion, but in my humble opinion, but I think the idea that this has been put forward in this paper is inspired by George Zawadzki. And in this regard, yes, I mean, it will be very exotic because we discussed that, they interpret generally this band structure as a result of Jean-Gray singlet and 3-spin polaron. To me, it's a very exotic explanation because you can get this picture by assuming just a bilayer structure and inducing some kind of a spin density wave transition on this. In their case, they even don't need it's a bilayer because it's essentially, Jean-Gray physics and the 3-spin polaron is a kind of, well, to some extent, maybe it is because, Jean-Gray singlet is in their case is a in-plane physics, while 3-spin polaron is a nickel and oxygen in between. So this is what they call a 3-spin polaron.
Between two layers.
Between two layers, yeah.
I see.
But in my opinion, I mean, one can do whatever you want in principle, but you can explain everything with much more, let's say, simple-minded explanation. Which again, for me, is making a lot of sense because you can do a lot of other things. You can explain superconductivity, you can kind of have, at least in your own head, you can have a consistent picture of what is going on. Whereas if you start from a 3-spin polaron and Jean-Gray singlet, it's you start from the scratch essentially, and you have to explain what is the symmetry of the gap, why this superconductivity occurs. While if you start with pictures that I presented, which is based on initial guess from DFT plus correlation, it somehow makes a lot of sense to you, no? Because you say, okay, there is a z squared, it's strongly correlated, it gives rise to some, correlation effects, maybe spin density wave, but it's coupled with x squared minus y squared. The S plus minus symmetry of the superconducting gap is also mostly comes from the z squared, and because it's an interlayer gap, and there is an interlayer exchange which gives rise so somehow there is a adiabatic transition from the weak coupling theory to a strong coupling theory. Somehow there are details, but there is a adiabatic continuation, in my opinion. While if you start from this very exotic explanation, then the question is, okay, is there any weak coupling regime of this? That's a question.
Yeah.
It's like in cuprates, we know that there were theories developed only for cuprates, which cannot be applied to anything else. And to me, this here looks like a similar ideas, like theory developed particular for bilayer nickelates. But we know that this kind of series you can develop for trilayer nickelates. You can also get, consistent picture. You can explain why TC is going down, right? Because in this case, you get this S plus minus pairing, but between these two outer layers, and that explains immediately why TC is so low, and so, this kind of things. But then, okay, so what happens in a trilayer in that case? How to transform this Shanghai singlet and three-spin polaron in the trilayer picture? I don't know.
Right.
Just to make sure that in your picture, the SDW is mainly carried by DDs.
Yes, it also carried mostly.
Yeah, CDW is mostly.
And CDW is mostly D square minus Y square.
And this is you call it the parent state of the S wave.
S plus minus, yeah.
Is there any implication on the parent mechanism?
Well, it's still supposed to be the interlay exchange. I mean, in a local language, it's an interlay exchange. Here, it is an odd susceptibility. So here we say this is an odd susceptibility because effectively what is needed is that you have a large separation between odd susceptibility is much larger with these wave vectors than even susceptibility. Sorry, I need to remove this one. Yeah, because effectively it's not a purely interlayer exchange. So it's basically, you see, the one is just somewhere the difference between intralayer and interlayer. But effectively, you work in the situation when interlayer fluctuations, antiferromagnetic fluctuations, are stronger than the intralayer.
There's some debate on the different roles, the superconductivity on two orbits.
Right.
And seems also.
Here is dz squared, right? Here it's dz squared. So essentially, okay, so I would say that even in a strong coupling perspective, it's not that different because in a strong coupling, they say the z squared is localized. However, without the z squared, you don't get superconductivity because x squared minus y squared is just quarter filled. So, so for there, z squared provides a medium. Here in the itinerant picture, it plays a very important role because this is where the gap is also the largest. But still, z squared is mostly correlated. So the only difference is that whether z squared is a medium or z squared is a player, right? But in both cases, z squared plays an important role. I am ready to accept a theory which says, look, z squared is completely localized. Well, one can take this. If you want, you can work with this. I mean, it would not it would not agree with ARPI's data on thin films, where we see that the gamma pocket does cross the Fermi level. Plus, there is another problem, is that along this direction, along gamma m, z squared antibonding and antibonding x squared minus y squared are completely degenerate by symmetry. If you can look at, I had this picture at the DFT level, right? You see that along this direction, the color is equal mixture, if you want, right? So the z square starts here, but then it comes back also here because it has to come back here by symmetry, right? Yeah. So in this regard, I would say you can take both point of view. So there is this proposal by Giniat Khaliulin, who is saying, look, z squared forms this triplon excitation, and this is how the pair, and then you have these two residual bands which participate, which have this coupling to this triplon excitation. It forms also D wave or S plus minus gap, but it comes due to the triplon excitation. That's probably an extreme of the model that you start here with. But it has a adiabatic connection, in my opinion, at least logical connection.
Right. So in their predictions, that the alpha should have
the largest gap.
Larger gap.
Also, I don't know whether it's really fundamental. I mean, maybe you can twist the parameters and get the larger gap on the beta.
It's just the mediate the pairing from beta pocket.
Yeah.
It has larger
density of states. Yeah, something like that. Yeah, in this, that's a problem of this two-band system, is that if you just have two bands, there is a condition that, when you write the gap equation, which is created by the interband scattering, it requires that the gap is multiplied by the corresponding density of states. And if the density of states on the beta pocket is larger, then it's true. It has to be on the alpha. In our case, it's not the case. We only overall globally require that the gap changes sign between bonding and anti-bonding subspace. In principle, what we also, I think in their case, the situation will change if they allow to have also intra-band interaction. Yeah, then they of course can change the relation between the gaps.
Right. Yeah.
About the second part, we mentioned about the Q equal to pi half and pi half minus pi half.
Yes.
And you say it's like you but from the calculation you did, you received some let's say some I mean, this two Q vector is not equal to each other, but it looks to me that
No, they are equal. I mean, they are by symmetry related.
yeah, by symmetry related.
Right, but they connect different state on the Fermi surface.
Yes.
So that's why they are
so
different.
Yeah, I agree that they can be different, but since we by our calculation result, we see the difference between these two.
If you do in the orthorhombic,
they-
I immediately agree. If you do the calculation in the orthorhombic phase, then they are no longer equivalent. Then you already from the very beginning already broke the symmetry.
Yeah, but so it would mean that if you
do it in a
gamma function-
tetragonal, if you do in a tetragonal state,
yeah.
in a tetragonal state, they will be identical because they are related by symmetry. Therefore, they will have the same
Okay,
size of the peaks.
so in the beginning, actually, we're not start from the picture where you showed firm surface before, right? Because before we see this firm surface, it looks very like C4 theta.
Well, in reality, it isn't. I mean, there is a structure of asymmetry, but it's so tiny. The difference between A and B is so tiny.
Oh, actually,
There
you don't
is-
have a
You
C4
don't have a C4 symmetry.
Okay, then
We don't have, we just plotted it here for convenience, but they are not exactly
now I
identical.
see it can actually get twisted a bit.
Right. But this is enough.
Okay.
This already gives you a difference between pi 0 and 0 pi.
Okay, because I see
It's a little bit twisted. Yeah,
Okay.
but it's hard to see with bare eyes. But if you do the calculation, you immediately see that pi 0 and 0 pi are
I
different.
just expect the firm surface to be like not C4 symmetry.
Right. If this is not C4 symmetric, then there is no problem. Then you immediately see that they are inequivalent. And that is why the system immediately knows which order it wants to set.
And just from the bare looking, I didn't
Right.
see.
Yeah, sorry.
Well, like,
Sorry.
Okay.
Yeah.
More questions? Yeah, I think I saw one online. He asked that in the first part, because you have done a lot of calculations for this from the SDW amendments. He asked, so how to determine the parent symmetry from this spectrum? Because now it's kind of under controversial.
Right.
So from SDW amendments is enough or not?
I would say that the way to do it is to perform the different height.
Mhm.
And that would give you already the position of the main gap, where the main gap is located on the alpha or beta pocket. And then in addition, it will also change this low temperature behavior. So you see in this case, you will be able, so the closer the tip is to the surface, you will be more picking up the x square minus y square orbitals, and the more you will see the V shape. So you need another, so you need a tip variation, or try to also not make a tip spherical symmetric. That's also a possibility. So basically try a different needle, essentially try different needle, or change the position with respect to the sample. So that would be, so you need another parameter.
Let's see.
Yes, good.
On this one. Basically here you propose change the Z
This-
for distinguish this. I saw sometimes people use the superconducting tip.
But that would be different. That would be, so what
That
you
would
can do
be-
this, right? I mean, you can do this, but what effectively, actually, you know, I believe, but maybe Jian Wang will not agree with me from Peking University, because he did also STM measurements. He actually did STM measurements on the samples that were produced by Zhou Chen group. You know, Zhou Chen groups, they did STM, they got more or less similar result. But in their case, the films degrade very quickly. So in order to do STM, they basically transfer it from one floor to another floor in a cryogenic condition, the films. But he gave the sample to Jian Wang, and that means they took it in the more or less maybe in vacuum, but effectively it was room temperature, and they had to carry it to Beijing from SUSTEC. And so then on the bare surface, he didn't see any superconducting gap. So what they did is actually they pushed the sample, the tip into the sample, and then took it out, and then they measure. And I believe they saw a superconducting gap, which is twice larger than this one. And my suspicion is that they accidentally did SIS tunneling, because effectively they pick up some part of the superconducting film, and then they measure SIS junction, and then of course you will see, and they saw a very different spectrum also, because if you look, they have a very flat region below, and they had really zero, and that's very unusual what they saw. So it's very unusual behavior of the IDV, and it would be also one of the things, but nobody did the calculation what you would expect in this case. So this is something we think about to do, but to do SIS, you need more efforts. That's true. So you need to do more variety, more different surfaces, different tips to make a conclusion. But we have ARPIS. Of course, ARPIS is unambiguous. So they see, and I think this is what more or less what we know now is that, you know, they see this gap, which is at least certainly that there is no D wave. And it's now appeared last week. So previously that was a statement by the SUSTEC group. That was the only group which made this statement. Now they see it in this other substrate, and they see that the gap is maximum here, has this value. So
Actually, the APES was done by the same group.
by the same group
In the Hefei.
in Hefei. Oh, okay. I see.
Yeah,
I see.
yeah.
I see. So at the end of the day, that's a different. But it's a different samples, right? It's a different sample, different substrate. Yeah, on a different substrate.
Great advantage is just they don't have pseudo gap here.
Yeah. They don't have a
Because
pseudo
in
gap.
the previous
They said
they have
that-
pseudo gap.
Yeah, they see a pseudo gap, and then you ask yourself, okay, is it really a superconducting one, right? But they saw it closes. Some gaps are closing at TC. So I think I mean, maybe Professor Puchunjang would not agree with me, but I would say that D wave is really difficult now. I mean, it can still be, because this was one of the argument, because if you look, I have the slide too, so I can, you know, in principle, you can, you know, yeah, you can go here, and then you can ask yourself, so this is a bulk. So bulk is somewhere here. Yes, so this is a bulk sample, sorry. So this is a bulk material. So this is the lattice constant of the bulk. This is a compressive strain somewhere here. It's in principle, because we know that there is a competition also here for unconventional superconductor. It's not unusual that the symmetry may change, because it's always an interplay of the interaction and the fermiology. So it can happen that under compressive strain, you get an S plus minus, and maybe for bulk, you may get for some reason D wave, because we don't really understand what means bulk, right? Because one of the argument is that we know more or less the lattice constant, but it might be that there is some local stress, local strain. This is what some people argue, and this is where superconductivity takes place. Maybe things change. I don't know. I mean, we need more experiment. We need more to know. For theory, it would be unlikely because we do see that the S plus minus wins for, I mean, this is also your calculation, that that under compressive strain and in the bulk, you very likely get an S plus minus. But if you think if there will be more evidence coming for D wave, I think this Andreev reflection is still too early to say something.
Right. So I have a last question about so if you combine all this superconductivity and then magnetic order, so there's a debate whether it belongs to the strong coupling region or is a itinerant picture. So what's your opinion about this?
I think what let's personally, I would say that probably because it's easier, but the weak coupling theory developed, in my opinion, now a consistent picture which allows you to go from the magnetic to the superconducting region because we have a method in hands which is allowing to treat you both, right? So there is a diagrammatic methods and you can do this, so either FRG or something else, even RPA, but it allows you to understand in a consistent fashion the all these phases. Now, on the localized picture, I think I saw mostly people did calculation in the tetragonal phase. Somehow what I think is missing is to do the calculation for the orthorhombic phase to show that you can consistently get the pi over 2 phase, and then you change the lattice constant and take your theory and get consistently the superconducting state to be dominant. Because what I saw mostly from this, it's always a play with the tetragonal phase. So people change feeling, say this is a mode, selective mode transition, so on and so forth. It's all very nice, but there is no experimental reference point. And in my opinion, there is two experimental reference point: bulk crystal at ambient pressure, because there is no ambiguity about the parameters, right? And there are thin films, which are known superconducting. So take these two reference points and consistently explain within your strong coupling theory, and then everything's fine. Because when I ask Ginyat, he only wants to talk about superconductivity.
No,
He doesn't want to explain magnetism. So in this regard, that's a question.
Yeah.
That's a question. So you need to have a theory which explains these two reference points.
Yeah. Okay, if no more questions, let's thank Professor.
Thank you so much for your
Ilya
patience.
Yeah. It's wonderful talk. Okay, thank you very much. It's a long talk.
Sorry for that. Yeah.
Yeah, it's very nice.
Yeah. So June, was very nice to see you. I hope you enjoy Nagoya.
Yes, thank you. Thank you very much for your last talk. Actually, I have one short question. Yeah. Could I ask one? Yeah.
Yeah. Others can.
Okay.
Okay, you ask question.
So I'm wondering, so
Ilya, you can take a seat.
So how shall we understand the different temperature dependence behavior of this density wave on bilayer and trilayer nickelate, right? This is. I'm also wondering why this in this trilayer system, this CDW is induced immediately after this maybe this SDW transition, but in the bilayer actually this charge only occurs at a much lower temperature. Yeah.
Actually, I don't. Let me put it like this. We just argued. I don't know whether you picked it up, but we just agreed that to some extent there is a similarity in which sense. If you look at the orthorhombic phase, then the magnetic wave vector is 0 pi. So if you try to take a double Q of it, you will get a 2 pi. So this will be exactly this intra-unit cell order because 2 pi is a reciprocal wave vector. So in this regard, this intra-unit cell order is the same double Q that you have on a trilayer, with the only difference that in a trilayer, the original magnetic wave vector is incommensurate. Such that you can still create a 2Q of this, and it will be not a Q equal to 0. Here it is not. However, what I don't have an explanation for you why they don't occur simultaneously. Again, within our only theory, there is no, there is no guarantee that it occurs together or it can occur at a lower temperature. In our case, we also see that we can tune them together, but then the order, the transition becomes first order. And I think it is first order in trilayer, right?
Yeah.
I think in a trilayer, we can check, but I think I was looking into this, but the statement was that in a trilayer, it's a weak first order transition.
Personally, I believe that that there can be coupling between the SDW and the charge density wave.
Right.
And by changing TC, maybe the thermology will change a bit. The coefficient of this coupling.
Yeah. It can be different, right? So you need you really need to do the expansion.
So maybe there's
So it's
chain.
Right. It can have some accidental. So I still believe that the physics is very similar. So you have a primal magnetic instability, and the charge density wave is a secondary instability, and it can be also viewed formally as a 2Q structure, except that in a trilayer it is a true 2Q structure, whereas in the bilayer, because magnetic wave vector is commensurate, the 2Q builds a Q equal to 0 state. Now, whether they coincide or not, it depends. In our case, I don't have this plot, but we realize that if we change the crystal field splitting, we can tune them to be closer to each other or separated farther strongly. So again, it's not universal. So in this regard, I think the physics is not that different.
I see. Yeah. So how about this temperature dependent behavior? Oh, sorry, the pressure dependent behavior of this.
Yeah. So we don't have, of course. So basically, we try to do different linearization as a function of pressure. But then the problem, it turns out that the changes are so little that when you try to do linearization for different pressure, you don't get a kind of a clear trend. So then we just took this crystal field splitting to be a parameter. And I remember that then if you can tune it in such a way that the charge density wave transition is going down, whereas the spin density wave transition is going up. You can find this regime. But again, it's not something, again, this is because, again, the statement is that, remember what I told you, and this is maybe something what I can say that this is more like a strong coupling picture, is that if you assume that the dz square is more localized, then of course you think that the main interaction is a super exchange. It's not in our theory, but if you try to make a picture of it, and then you put the layers when you introduce the coupling, when you introduce the pressure, the layer come closer to each other. So the super exchange has to increase initially first. And this is why the transition temperature into the spin density wave state will go up.
Yeah, actually, this point is kind of tricky, if you consider this kind of strong interlayer exchange coupling, right?
Right.
They form this kind of interlayer singlet. It's kind of increasing this kind of exchange coupling is detrimental to in-plane order in principle.
To interlayer, right? Because I told you this, right? So this is a strong coupling calculation, you see? So that is what is shown on this slide, right? So you see that here they claim that once they go once they increase the pressure, the J-perp is increasing.
Yeah.
And that partially also because once you increase the pressure, you also see in this calculation that NZ squared wants to become half filled. Yeah. So in this regard, it's clear that it goes up. So in this regard, you understand why T spin density wave is going up, because J perp is going up. So that is somehow the interpretation. And you will also get it, by the way, in your weakcoupling theory, if you just shift the doping. So if you just assume that with increasing pressure, the filling of the NZ squared, you just by hand or by crystal field, you increase such that it becomes more a half field, you will see that the spin density wave transition is going up.
Okay.
This is what you can try to see also. Actually, what is known about the trilayer? Do you know if it's in a trilayer?
I think it will decrease.
It will decrease
with increasing pressure. Yeah. Yeah, there's a
Yeah,
kind of slightly different.
Yeah. There, I think it's different. So it could be that there it's more itinerant than here. That's also a possibility. But it's really unfortunately, in these values of pressure, you cannot reliably make a DFT calculation which would give you, because the changes are so tiny that it's very hard to pick up a main trend.
Nice. Okay, great.
Okay, June. So have a nice time
Thank you.
in Nagoya. Yeah. So maybe we see each other.
Yeah, also, we wish you a nice day in Beijing, nice and fruitful stay in Beijing.
Yeah. Okay. Bye-bye.
Yeah, bye. Yeah, see you next. Yeah, see you next time. Bye.
Okay. Thank you so much for your time.
Yeah. Also, thank you very much. Yeah. Bye.
Bye-bye. Bye.
So I will. Yeah.